Here's a fluid mechanics question that is actually quite difficult if you try to solve it in the classic way, which is using Newton's second law. You can do it, but it will take a good amount of time. But if you're being a bit observant and if you notice a couple of things that are actually going on, you will shorten the amount of time it takes to reach the solution significantly. And that's what we're going to try and do to this question. This is the kind of problem in fluid mechanics that you might get as a first year undergraduate student who's doing something like aerospace engineering or mechanical engineering or ship science or maybe even civil engineering. Or it can be something that you can get in high school if you're preparing for some kind of physics competition. And if you have any suggestions for any similar problems that you'd like to see on the channel, let me know in the comments. So here's what we know. We're dealing with a cylinder which is uniform. Now, uniform means that the density of the cylinder is the same at all points. And we don't know the material, we don't really care, as long as we have the density, which is 250 kilograms per meters cubed. And the cylinder is being held at rest such that the upper surface of the cylinder is touching the free surface of the liquid. And it's being held in place, so it doesn't just stay like that by itself. It is held in place by someone's finger, and that person is pushing the cylinder down just enough so that the entire cylinder is just submerged beneath the free surface. And we know a couple of things. So we know the length of the cylinder, which is this side, is 20 centimeters. So as usual, as I tell all my students, you should always convert this to SI units, which is meters in this case. And the radius of the cylinder is 3 centimeters. So let's actually do it like that. So that would be R equals to 0.03 meters. Okay, and what we have to find is the velocity with which the cylinder leaves the water surface. So this is, yes, this is a hydrostatics question, but the object itself is moving. So it's a hydrostatics question in the sense that the liquid is stationary, but there is some motion for the object. And then we also know the density of the water being what it is, so 1,000 kilograms per meters cubed. We can approximate the gravitational acceleration to 10 meters per second squared, and that's it. Okay, so while you can do this with Newton's second law, we're not going to do it this way. We're going to try to notice something going on here. So let's say that this person, let's say this person releases the cylinder. So when that happens, what you would expect is because of that downwards force acting on the cylinder. So this downwards force was necessary to keep the cylinder in place. So this means that the cylinder had a tendency to go upwards. So if you remove that force completely, that's what the cylinder will do. So the cylinder will start rising. And let's say that at this moment in time, the cylinder is located at, well, let's say the cylinder is submerged a certain amount x underneath the water surface while it's still going up. What I would like to do is I would like to find what's the upthrust. So in other words, what's the FB here? So the AFB, as usual, is the weight of the displaced liquid, which is the density multiplied by the volume of the displaced liquid multiplied by G. So this term here, VD, this is the volume that is the volume of the cylinder under the water surface, which is how much volume of cylinder is submerged at this moment in time. And we can actually rewrite it like this. So this is rho 0. Instead of VD, I'm going to express this in terms of the volume of the cylinder, which is S, or if you want, pi r squared, because that's the cross-sectional area of the cylinder multiplied by X. And then, yeah, the whole thing is VD. And then we multiply this by G. Right, now let's rearrange this in a certain way and we'll actually see what we have. So FB, the buoyant force, is going to be rho 0 and then we have pi r squared, and then we have g, and then we have x. So I move the x at the end because x is actually the variable here. This thing is constant. So no matter where the cylinder is along its journey through the water surface, right? This term that I drew here in a blue rectangle is constant. So the density of the water is constant no matter what. The cross-sectional area of the cylinder is constant. G is constant. The only thing that changes is x. And how does x change? Well, x depends on how much cylinder is beneath the free surface. So if the cylinder rises more, x gets lower. So if x gets lower, it means because this is constant, this will get lower as well. But the point here is that this whole thing in blue, this can be called k. Just give it another variable name. So the equation above becomes fb is equal to kx. So where have we seen this before? Well, this is actually the same as a spring force, isn't it? Because if you have a spring, then the elastic force in the spring is proportional to the displacement, and we usually write it as kx. Right? That's what we call the force, the spring constant times x. So while we're not actually dealing with the spring in this question, because the buoyant force, because the force due to the water equals a constant times the displacement, we can treat the water as a spring in a way. So if we can do that, it means that while the object is submerged, it has an elastic potential energy, where the equivalent, now obviously the water is not the same thing as a spring physically, but from a mathematical point of view, this here is an equivalent elastic constant. So this is K equivalent. So if you remove the water altogether, and if you replace the water with a spring, which has a spring constant equal to the water density times pi r squared g, then the problem would be identical. So we're going to use this and combine it with the idea of energy. So if the water acts like a spring, it means the object has elastic potential energy. Elastic potential energy like this. So we're going to apply conservation of energy, therefore, and this is how you get to the answer much faster. The reason I spent some time here is to sort of give you an idea and to try to make you understand that the water is, from a mathematical point of view, acting identically to a spring. So there is no drag in this question. So as the question states clearly, at the end, neglect all dissipative effects, which means that we basically ignore friction. So if we ignore friction, which would be the only way in which the total energy would be reduced, it means that the energy of this object is conserved, and that's what we're going to apply. So let's first of all draw the object before it leaves the surface. So this is the object just as that finger is removed from the diagram, of course. Okay, so we have the object here, and this is where the object will start going upwards, but it's just before it starts moving, and this is the object in the final scenario. So this is the object as it leaves the water surface. So the water free surface is here, and we have the free surfaces here in this case. And what the question is asking us to do is to find the velocity here. So what's the speed, what's the velocity of the object in this scenario when the bottom side of the cylinder is touching the free surface? So let's do a conservation of energy. We're going to say that the total energy here, so the total energy in scenario 1 is going to be equal to the total energy in scenario 2. Now, the total energy in scenario 1 is based purely on elastic potential energy. So that's going to be 1 over 2 times K equivalent times X. Now, X is how much cylinder is underneath the water surface, which at first is the whole cylinder. So now my potential energy is going to be this L squared. And by the way, the elastic potential energy is just 1/2 kx squared. So my x is the displacement, is how much cylinder is underneath the free surface, so it's L squared. In this scenario, the total energy has actually two components. So first of all, there's no more elastic potential energy because there's no more cylinder underneath the water surface. So we have kinetic energy, which is 1/2 mv squared, but we also have gravitational potential energy. Okay, so keep in mind that in terms of potential energy, there are two types. So there's gravitational, and then there is elastic. Okay, so in this case, in the second case, we don't have any more elastic potential energy, but we do have gravitational potential energy because the cylinder moved upwards. And with respect to this initial position, the cylinder climbed an amount L, of course. So the gravitational potential energy is mgl. There are no dissipative effects, meaning that this energy is equal to this energy. So we're going to write that here. So we have in the first instance 1/2 ke L squared is going to be equal to 1/2 mv squared plus there's not 1/2 here, there's mgl. And that's what we're going to use to find the final answer. So let's actually substitute Ke. So Ke is essentially this thing here. So it's rho 0, and then we have pi r squared, and then we have G, and then this is multiplied by L squared, and that's equal to 1/2. Now instead of m, which is the mass of the cylinder, I'm going to substitute this with density times volume. So we know the density of the cylinder is given to us as rho, then the volume is pi r squared times L, and that's the mass, and that's v squared. And we're gonna use this again here. So that's density times pi r squared times L, and that's gonna be times GL. Right, and that's what we have. So what you should notice is that we can cancel out pi r squared because it appears in every term. And at this point, it's just a matter of rearranging to get v, or v squared for now. Okay, so I'm going to make this term, I'm going to write that term by itself. So we have 1/2 rho L v squared is equal to, I'll move this to the other side. So it's 1/2 rho 0 GL squared minus rho GL squared. Right, so we're trying to get rid of this part. So I'm going to multiply everything by 2 over rho L, just to get rid of that coefficient of v squared. So we end up with v squared equals, and this is what we have, 1/2 rho 0 GL squared times 2 over rho L minus rho GL squared times 2 over rho L. So here the 2's will cancel out. This L will cancel out with one of the L's here, and then this rho will cancel out with this rho, and then this L will cancel out with this L. So we have v squared is going to be equal to rho 0 over rho GL minus 2GL, which is GL times rho 0 over rho minus 2, which means that the velocity is just the square root of that. So it's the square root of GL times rho 0 over rho minus 2. Now, here's a good reason why you may not want to use numbers from the beginning of the question and just stick to symbols. When you get to this point, you'll instantly know that, well, you won't know if this is the correct answer, but you'll know that this answer has the correct units because this is meters per second. So the right-hand side should be in meters per second as well. So this is meters per second squared multiplied by a length which is in meters. This thing doesn't have any units because it's density over density, which is just a number, so no units. And the whole thing is square rooted. So it's square root of meters squared per second squared, which is meters per second. So the units are consistent on both sides, which is a nice quick way of giving feedback to yourself. And if we substitute numbers in here, we should get that the velocity is 10 multiplied by L, which was 20 centimeters, so that's 0.2, multiplied by, so this was 1,000, and this was 250. So 1,000 over 250 is 4, and then you have 4 minus 2, and then you have 2 multiplied by 2, and the answer is 2 meters per second. And that's the final answer to this question. So, oh, and another reason why you may want to keep symbols all the way through is that in the end, you will be able to see how each variable affects the answer. So right now, I can instantly say that if my cylinder was 4 times longer, the velocity would have been twice of what I got here, right? So this tells you that the velocity is actually proportional to the square root of the length of the cylinder. And also, if you have done enough physics problems in the past, you would have noticed that this result looks very similar to the result of velocity when you throw an object vertically, when you drop an object a certain height. So when you drop an object over a certain height, like this, then the velocity at the bottom of the drop is going to be the square root of 2gh. So see this term of gh, or g times the length in this case, appears and seems to be consistent across different problems. And this is another benefit that you get from using symbols that you cannot get if you just put in numbers from the very beginning. So there we have it. So we have the cylinder that is being released. And the key thing here was to notice that the water, from a mathematical point of view, acts like a spring. And it creates this sort of equivalent spring constant, which is equal to this. And then by using conservation of energy, we can obtain the answer relatively quickly. And we have this nice 2 meters per second at the end. And that's the end of the question.